How'd it go? Okay. Could have been worse. C, I'm curious really about C. What you guys thought of C? Not saying A and B were easy, but I'm very curious what you guys did on C. So I'm going to show you guys. Actually, I think their rubrics are really good. I don't think their rubrics are great on this one. And so for B and C, I did my own to kind of give you guys some tips, but I'm going to show you the rubric for A. A was, we didn't do any, maybe one last time, but A is the one when you're trying to find that area outside of one curve and inside the other, when you do kind of like the outside one squared minus the inside one squared. So that's that. Don't forget about the 1/2 out in front. So they're just integrating from the two intersection points, pi over 3 to 5 pi over 3, and then r squared minus r squared. That's worth 3 points, which is surprising, but 3 points on that one.
Hey, Mr.
Don't
Dean,
work it out. Yep.
are we supposed to be seeing the rubric?
Yeah. What do you see?
The problem.
Horse poop. Let me try again. What about now? Good? Awesome. I'm awesome. I'm the technology.
Yep.
All right. So on B, here's what first of all, the answer to B is 2/3. But I would never get to that point. Here's what I would do. If it were me, I'm going to give you my biggest advice here. So we're trying to find dy dx when theta is pi over 2. I think that's the question. Yeah, pi over 2. So you can either have the formula memorized for dy dx, which I will never have that formula memorized. If I have to do this problem, I trust myself to know product rule and I'm quick enough that I can just do the stuff and not have a ton of time. So I found dy d theta. Remember, y is r sine theta, so plug in r. X is r cosine theta, so plug in r. And then I did product rule on both of them. Then the biggest time saver I could give you, again, if this was me doing the FRQ, this is what I just did over here. It probably took me a minute maybe to do this. Then dy dx when theta is pi over 2, I just plugged pi over 2 in for all the thetas and I moved on with my life. No way am I going to start analyzing or evaluating any of that stuff. It's too easy to make a sign mistake, just do something stupid, and you lose your credit when that gets you 100% credit and saves you a ton of time. But if you did keep going, did anybody actually go all the way and get 2/3? Yeah. So that's the answer. It's not wrong, but just keep in mind, it is easy to make a mistake and it is easy to just lose a lot of time when you start doing that stuff. Pi over 2 is a nice one to work with. So pi over 2 is not going to take you a ton of time anyway, because it's zeros and ones. But if that was like pi over 3 or something, you don't want to spend time messing with all that junk. So that's that. Now C is interesting. You know, the first time I read C, I was like, holy smokes, what is going on here? And then I looked at the rubric and I was even more confused when I looked at the rubric. And then I slowed myself down and I was like, wait a second, let me just think through this. This is a related rates question. And the quicker you can recognize that, it makes this problem so much easier. It looks tough, but if you can realize, okay, they're telling me the rate at which something is changing and looking for the rate at which something else is changing, that's related rates. And that's dreads. If you run through your dreads acronym, then this problem is not bad. If you remember dreads, the first D is a drawing, which they already give you, so throw that out the window. Now, the R, here's where it starts to get interesting. So R is you list the rates, the one you know and the one you're trying to find. You have to use some context clues. When they say the distance between the particle and the origin increases at a constant rate of 3, what does that say? Units per second. That's dr dt. R is the distance between the particle and the origin. So that's dr dt. And that might be the hardest part of the problem is recognizing that. So you know dr dt is 3. And then the one you're trying to find, you're looking for the rate at which theta is changing when theta is pi over 3. That's R in dreads. That's the rate I know. That's the one I'm trying to find and when I'm trying to find it. Now I need an equation that links R and theta. That's what E stands for. Well, thank you, problem. They gave that to you. They gave you the E part. The next part is we differentiate with respect to time. In dreads, once you have your equation, and the other thing to keep in mind, it's been a while since we've done these, but you need your equation to only be in terms of the two variables that you're dealing with the rates. You know, we did those, like we did some cone problems where you had to like change your height to be in terms of radius and stuff to get that to happen. This is already in terms of r and theta, so that's good. Then you differentiate with respect to time. So remember, you differentiate everything, and then you put d whatever dt. This is you kind of stopping time. So the derivative of r is dr dt. The 3 goes away, and then this is -2 sine theta d theta dt. All the hard stuff's over. Now it's just substitute your stuff in and solve. So I know dr dt is 3, so I replace that with 3. And I'm looking for d theta dt, and they tell me theta is pi over 3. And if you really wanted to, I got all the way to the answer, but honestly, if you just divided both sides by -2 sine of pi over 3 and left it like that, like -3 over 2 sine pi over 3, you get full credit. You do need to make sure, I think it says indicate units of measure, so your units are worth 1 point. So it's either one of these answers, but it's radians per second. Theta is measured in radians, and the unit of time is in seconds. Kind of a fun one. That one's worth 3 points. They're each worth 3, by the way. Here are the rubrics. I don't like the rubrics. This is B. That whole middle thing right there is B. They show 2 different ways to do it, I guess. I don't remember what they did, but I don't like it, whatever it is. So that's besides the point. And then here's their thing for C. It's just going through dreads, but they're using a lot of different like derivative notation and stuff. So anyway, what do you guys think? Anybody get a 6 or higher? Anybody at home get a 6 or higher? Nice. Very good. Okay. Well, this is why we practice. Perfect practice makes perfect, right? Okay. I want to make sure we have enough time to do the lesson and the practice FRQ. If you have homework questions, I'll do that towards the end. But I do want to make sure that we get through the other FRQ. We should have time, but so let's dive into the lesson today on Euler's method. Euler's method. E-U-L-E-R''S. Euler. Euler's method. Michael, are you ready? Are you ready? You're very ready. Oh, I wasn't expecting that. Let's do it. Me too. I was tired this morning. I was more tired this morning than normal. Normally my alarm goes off like, and I'm like, pooh, let's do this. Today, not that way. I don't know why. I think I stayed up too late Saturday night playing cards. I think that's what happened. You guys know Mr. Cecil at all? Play cards at his house Saturday night. Kept me up too late. I don't like it. I like to be asleep like before 9:30 every night. And we play cards till like 1:30. It's like, oh gosh. And then of course the dog gets up at 5. You know, whatever. Okay. So before I dive in just straight to the notes and the lesson, I want to kind of explain what this is all about. Okay. Back in semester 1, we learned how to do tangent line approximations. If you remember what we would do, so let's say that I have this curve and I know this point right here. I know that this curve goes to the point 2, 1, okay? And the other thing I know is the derivative of this curve. Now here's the thing, when you do tangent line approximations back in semester 1, technically in AB calculus, every differential equation that you guys get pretty much can be solved through integration. You can separate the variables, then you can integrate. Technically, you could find the original function, and then you don't need to estimate at that point. You could plug the x value into the original function and find the actual value. Well, now in BC and moving forward in your math classes, what happens is you get differential equations that can't be separated. Like anytime your differential equation is in terms of addition or subtraction, you can't separate those things. Like you couldn't subtract y over and then have like dy minus y. Like you can't integrate that. So if your differential equation is not separable, we can't find the original equation. Okay, so first semester, here's what we would do. Let's say I wanted to find the y value here at 3, okay? I want to approximate the y value at 3. Well, first semester, here's what we would do. We would say, okay, well, let's find the tangent line through this point. And then now that I know the tangent line, I could just plug 3 into that tangent line and say, that's a pretty good approximation. Well, the problem with this is if I found the equation of this tangent line and plugged 3 into it, I would be finding this y value right here at 3. Is that y value pretty close to that y value there? You guys tell me. You can shake your heads. You all know the answer. Yeah, no, that's a terrible approximation, right? So here's what we're going to do instead today. Enter Euler's method. If we want to find a value farther away from this point, like if I was looking for this y value here, then a tangent line approximation would be the way to go. I would do my tangent line, I'd find the tangent line value, we'd be hunky-dory. But if your point that you're trying to find is farther away from the point you know, here's what we do instead. We do need to find the first tangent line. But what's going to happen is this. Imagine that, you don't need to write any of this, I just want to explain what we're doing. Imagine that I found this value right here. Okay? I found that y value and that x value right here. And then let's say I stopped and I took that ordered pair and I found the slope of this curve at this point. Like basically now imagine that the slope of this curve would be right here. So imagine I found the derivative at this point and now it looks like this. And then let's say, okay, now what if I want to find this point here on that new line that I just found? Okay, well then I can find the slope at that point that models the curve and find a new line that's going to have the same slope as the curve like this. And then I'm like, okay, what if we want to stop here, find that point? All I'm doing is using lines to plug these points in. That's all I'm doing. I'm finding a line. I'm plugging in an x value and getting a y value. Then I find like a new line at that point. And then I plug in a new x value. And that's what's happening. Now, if I found the slope of the curve here at this point, see how that slope looks like this, and just used right here, then I found that point. Then I could say, oh, that approximation is a lot better than this approximation right here. Essentially today, instead of doing one tangent line approximation, we are going to be doing multiple tangent line approximations within one problem. It is not difficult, but that's the concept. We are going to find a tangent line. We're going to plug in an x value and find this point, and then we're going to stop and be like, okay, let's find the tangent line at this point. And that's what this is. And then we're going to pick a point and stop, new tangent line, pick a point, new tangent line. Now, the nice thing is you're only ever going to have to do like 2 or 3 tangent lines. I just did 1, 2, 3, 4 here. You're only ever going to do 2 or 3. That's the concept. Instead of doing one tangent line that gets us way off from the actual value, we're going to do multiple tangent lines, kind of like walking along the curve is what we're doing. We're walking along that curve to try to get close to that point. That's the plan for today. So let's go to Euler's method notes. We don't have a ton of examples. In fact, just 2 or 3. And then an FRQ to kind of show you what you'll be asked to do. When you guys go to college, you'll take a class, if you're going into math, you'll take a class called differential equations. Like that's the title of the class because there's so much that goes into them. And that's what we're dealing with right now are basically differential equations that can't be separated. So all this stuff will come back again in college. I remember really enjoying that class. I couldn't tell you one thing I learned in that class. Like I don't remember one thing, but I remember as I was in it, I didn't hate it. There were some classes I remember hating, and that was not one of them. So anyway, all right. So Euler's method, and again, this is just showing you kind of what's happening. We're finding a tangent line. We're going to break off of that tangent line to find a new one. We're going to break off of that to find a new one, all to approximate a point on the curve that's kind of far away from the point we know. That's the generality. All right. So it says, use Euler's method to approximate the particular solution of the differential equation. And y prime, if you guys remember, is just dy dx, means slope, passing through 0, 1, using a step of h equals 0.2. And I'll explain what that means. Now, part A says perform 3 iterations. You're never going to see it phrased that way. So before I do this problem, I want to show you guys how your questions will be phrased. On example 2, this is what you guys will see. They're going to give you a differential equation. They're going to give you an initial value. They're going to ask you to approximate the function. And then they're going to tell you kind of the other information. It says with 2 step sizes of equal length starting at x equals 2. That's how you guys will see the question pretty much every single time. Okay. So it's not going to say perform 3 iterations. But here's what we're going to do. The first thing we're going to do is find the tangent line at 0, 1. That's how we're going to start. We're going to find the tangent line to this function at 0, 1. Well, to find a tangent line, we need a point, which we have, and we need the slope at that point. So I'm going to plug 0, 1 into the derivative. That's what the derivative part does for us. It finds the slope at these points. So I'm going to plug in 0, 1. And so at 0, 1, my slope is -1. So at 0, 1, my slope is -1. And I'm going to write my tangent line. So it would be y minus 1 equals my slope, and then x minus 0. Nothing I've taught you is new at this point. We've done this. Now what we're going to do is this. It says use a step size of h equaling 0.2. Basically what that means is from the first x value, well, if you look at b, this will make it make more sense. We're trying to get to approximating the function at 0.8. So when they say use a step size of 0.2, they're saying walk along this curve and every time your x changes by 0.2. So here's what we could do now. If I wanted to approximate this tangent line, well, and it's 0.2 away from this x coordinate, basically what I want to do right now is plug 0.2 in for x. I want to use this tangent line to approximate the function at 0.2. So I'm going to plug 0.2 in for x right here. So it's going to be y minus 1 equals -0.2. And then add 1. So 0.8. So what that means is where we are, we started at 0, 1. Now we marched along this curve, and now we're at the point 0.2, 0.8. And we do it again. We found the new ordered pair. We're stopping. That's like where we're stopping. That would be, if you're looking at this diagram, that would be like what this is. We found the first tangent line, and now we found this point right here. Now we need to stop and do the same exact thing. From there, we just repeat the process. Start over. Now imagine I wanted to find a tangent line at 0.2, 0.8. So I got to find the new slope. So I'm going to plug 0.2, 0.8 into the derivative. So 0.2 minus 0.8 is -0.6. I write my new tangent line. So y minus 0.8 is -0.6, x minus 0.2. You're probably not going to have to mess with the decimals that we're going to be getting on this problem. This is messier than what you'll ever have to do. So I'm going to give you a lot of these decimal values yourself. But like I said, you're not going to have to do a lot of these messy decimals. So here's what we have. Now I want to use this tangent line. Now what am I going to plug in for x? 0.4. Each time I'm plugging in a number that's 0.2 bigger than the previous. That's what this is telling me right here. The first time I plugged in 0.2, now I want to go 0.2 farther than that. So now I'm going to plug in 0.4 for x right here. So y minus 0.8 is -0.6, And then 0.4 minus 0.2 is 0.2. Again, I'm going to give you these values because you won't have to deal with this stuff. But so we basically get y to be 0.68. You know, how I wrote it on the key, I actually like how I did it. On that first one, so you could see the ordered pair quickly, I did this. I said y of 0.2 is 0.8, and that kind of shows you very quickly what your next ordered pair is. So this time it's y of 0.4 equals 0.68, and so we can see our next ordered pair a lot quicker. I like how I did that. And then we do it again. Like I said, typically you'll do 2 iterations. It'll have you do like 2 times, maybe 3, but typically 2. So now I got to find the slope here. I'm going to give you these values. So I'm going to plug in 0.4, 0.68 to my dy dx, and we get m to be negative 0.28. And I do my new tangent line. I don't really like calling it a tangent line, but I think that makes it make most sense in your head. It's not really a tangent line. We're not touching the actual curve. So it's wrong to say that, but that's my new tangent line. And now I'm going to plug in 0.6. So I plugged in 0.2 initially, then 0.4, now 0.6. And if you look at B, we're already working our way to answering B. B says approximate y of 0.8. So we're heading there. I care more about answering B than performing 3 iterations. You'll never see that actually phrased that way. So now I'm going to plug in 0.6. And if you plug in 0.6, you would end up getting 0.624. Then the last time we do it will be the answer to our question. We're trying to figure out what y of 0.8 is. So the next one will answer part B. So now we're at 0.6, 0.624. Find the new slope there. Negative 0.024. The only thing I don't like about the problem is those decimals, but I've said it several times. You're not going to have to deal with things like that messy and gross. So as long as you understand like what we're trying to accomplish here, which we'll find out because you'll get one more you're going to practice here, and then we'll do an FRQ. And we're done with the lesson. Euler's method. I think I mentioned it the other day, but this is what they do in hidden figures to solve whatever the problem is at the end. I don't remember what they were trying to do. Were they trying to get back to Earth?
They were trying to calculate the, so they figured out how to get it so the rocket would be in orbit, but they needed to figure out a way to convert the angle of entry from orbit back into the angle of entry from breaking orbit. So they figured out how to, using Euler's method, calculate where they would land.
Oh, so they were doing a bunch of like these things to basically trace along a curve, like the route. Oh, well, that's cool. Because she had a whole bunch of stuff on the board. Like she was doing this times 100 worth. For them. Smart people. Vincent, I watched that video of the lightsaber. That was really cool. And it's going to be pretty deadly. I'd hate to be on the other end of that. We were talking about they're making real life lightsabers last time after you guys logged off. And oh, that was awesome. All right, I want you guys to try this. So what should your step size be on this one? How far should you go each time?
0.5.
0.5. Yeah, you're starting at 2, you're trying to get to 3, and it says you're doing 2 steps of equal length. Euler's method. Man, it's ancient. Is that Parsons? That's Sheldon.
Yeah.
I stopped watching Big Bang Theory once they had a kid. I watched like all the seasons, and then they had a kid, and then it was too real. And I was like, that's not as fun. Here's the answer if you guys would like to see it. If you're done. I would make sure, so it's not a very difficult concept, but I would make sure that you are keeping your work pretty organized. If you just have like different equations all over the paper, like they want to see the iterations. They want to see you kind of doing step 1, step 2, step 3. If you look at rubrics, they do these a little bit differently. But I put on that message board last year, I think. I said, what if my students do it this way, what would they need to show? And they just said, keep your work organized and kind of show walking along each iteration like this, and you'll get full credit every time. Questions? Make sense? Okay. I will trust that it makes sense. Then we're going to do an FRQ. Number 2. You ready? No one got 6 on the warm-up. Well, no, I lied. No one in here got 6. But here we go. From 2013, FRQ 5, no calculator. How much time do you guys want? I'll give you 10 minutes. That should be enough. 10 should be good on this one. This one's not as lengthy as the polar one. Only 11 more lessons, I counted. Only 11 more things to teach you guys.
That's tragic.
Yeah. And they're all kind of related.
Oh, that sounds like a bad pun, like we're going to early degrees with differentials.
That's not what we're doing. Can you guys at home see that whole thing? I guess it's on Canvas, but. Bless you, child. You guys good on time, or do you need another minute? Need a minute? Take a minute. On B, I'm getting a different answer than the rubric. But I can't find my mistake. It's got to be with the fractions. Right? I'm going to get negative 3/16 on B. You did. Anybody get negative 11 over 32? That's what the rubric got. You have to show me what I did wrong once I put it up. Can't. I got the right first point, 1/4 negative 1/2. What'd you get for the slope? You get 5/8? I did too. Y plus 1/2 equals 5/8 times x minus 1/4. And then you plug in 1/2 for x, right? Oh my God. I said 1/2 minus 1/4 is 1/2. Well, poop. All right. So that's 5 over 32. And then minus 16 over 32. Okay. Okay. So I picked this one for a couple different reasons. Number one, because it had an Euler's method on it, and that's what our notes was about. But the other reason was mainly for part A. C is kind of just I'm glad I have C on here because C is one of those where it's worth 5 points. You got to separate, integrate. There's a lot that goes into it. So that was just kind of a bonus. But A is kind of A and B are the main reason. So we've talked about L'Hopital's rule in here. We've talked about L'Hopital's rule, right? Where if you, right? Where you plug in the value, and if you get 0 over 0, then you can use L'Hopital's rule. And you can take the derivative of the top and then the bottom and then redo direct substitution. But here's what I haven't talked to you guys about yet. I didn't want to until a little closer to the AP. So here's what you're not allowed to do. I'm going to show you the answer, but here's what you're not allowed to do. You can't do this. This is what they have said. The graders have said this. You can't take the limit of, and then it's f of x plus 1 over sine of x. You cannot say equals 0 over 0. You cannot write that statement. You cannot write the limit equals 0 over 0 because this is not really true. Like 0 over 0 isn't a defined thing. It can't equal it. So here, if you have a L'Hopital's rule problem, which in all honesty, I'm not going to say with 100%, but probably if you guys have a limit question, especially on an FRQ, it's probably going to be L'Hopital's rule. Okay. There's not a lot of other limit type questions they can ask you that have some meat to it. So here's what they want you to do. They want you to show that the limit of the numerator, just the numerator, the limit as x approaches 0 of the numerator is 0. And the reason it is because if I plug 0 into f of x, they tell me in the setup f of 0 is -1. Like they tell you that. So this equals 0. Then they want you to show the limit of the denominator as x approaches 0 equals 0. These are both two true things. It's kind of the same as saying this without being mathematically illegal. So I'm not a big fan. I don't know how much I agree with it, but they do say you will not get credit if you write this statement here. So since this is true, then you say, so by L'Hopital's rule, the original limit equals the limit of the derivative of the top and bottom separately. So then you differentiate the top, which is just f prime, differentiate the bottom, then plug in 0 again. Now you're still not done because you got to figure out what f prime of 0 is. Well, f prime is the original derivative that they give you. dy dx, guys, is f prime. So when they say find f prime of 0, they're saying find that dy dx when x is 0. And when x is 0, y is -1. So you're basically plugging in 0, -1 for the derivative. And that turns out to be 2. So then you get 2 there. So while we talked about L'Hopital's rule, that's how you can officially do the work, do the process. You have to show the limit of the top is 0, the limit of the bottom is 0, then jump into L'Hopital's rule. But do not write this. They've said that's a big fat no. Please do not do that. On B, here's my work, the correct work, after Kamala helped me out because I feel like a nincompoop. Although I walked around, a lot of you guys had some trouble with the fractions. But here's the work. So at 0, -1, plug it in, you get the slope to be 2. There's my tangent line. Now, they don't directly tell you what your step size is, but you're trying to approximate 1/2, and the step size is 2. That means you have to go by a 1/4 each time. So I plug a 1/4 in, and I get -1/2. That's my new ordered pair. Then plug that in to get your new slope, tangent line, and then just plug in 1/2 correctly and do some fraction work from there. C is kind of the fun one. It's 5 points. If you didn't separate, you get 0 out of 5. But you do, here's the crazy part. If you don't separate, you get 0 out of 5. If you do separate, not only do you get a point, but you're probably going to get 2 or 3 points out of there because you're going to know how to integrate these things. So, I mean, it's such a huge difference between separating and not separating. So to separate, divide by y squared, move the dx over. Now we integrate both sides. On the quiz that I handed back in here, some of you guys were trying to do this with natural logs, but remember y to the second when it's on bottom is just y to the -2nd and then do your power rule. You only have to put plus c on the right side. Don't forget plus c. So if you got to here, you got 3 points already. Now plug in the initial condition to find the c value. Then you have to solve for y. You don't have to get to this point right here. If you just had this, then you're in good shape. Make sure you do solve for y. Get down to here. What do you guys think? And then I was curious, you don't have to know this, but I think it's interesting to kind of make the connection. You know, at the very beginning, I said, technically, if you can find the original function, you don't ever have to do like tangent line approximations. You can just use the original function and find the actual value. So I was curious. I took 1/2 and I plugged it into the actual function right here. And the difference between the actual value and this Euler's method value was like 1/10. It's like 0.1 off. It's a pretty good approximation if it wasn't separable. So anyway, all right. We are done. So you guys have 2 things. Number 1, you have an FRQ for homework. That's it. I put the rubric on there. So that way you just get more practice. You can't do enough free response questions. Just the more you see, you start to see patterns, you learn how to get your points. That's what you guys are doing. On Wednesday for e-learning, I have a review guide for you guys. It's pretty good in terms of how AP style it is. So that's what you guys have Wednesday. I'll publish it now though. So if you want to do it anytime between now and Friday. Well, you guys in here, you don't take your test till next Tuesday, right? Yeah. So yeah. But you guys at home, you'll want to do it Wednesday. So, all right, I'm going to publish that now before I forget. You guys are free to go at home. 20 minutes early. You guys get a 20-minute break. Farewell. Okay, stop recording.